Good evening again, Gloucester Severn. Exploring the Solar System Part 3, how we explore the solar system using telescopes on or close to the Earth. So, telescopes have been around for about 400 years or so, and I'll give a very brief history of how they've developed. I'll say a little bit about our first views of the solar system and a little bit about our latest views of the solar system. And then I'll be trying to answer the question, well, what next? Where are telescopes heading in terms of their development? So we know that telescopes have been around for 400 years. Galileo didn't necessarily invent the telescope, but he was one of the first to point a telescope to the sky and realized that we could learn a lot about how the world or the universe works by using this magnifying set of optics. Since then, telescopes have been getting ever more sophisticated and, generally speaking, larger. The objective lens, or ultimately mirrors that collect the light, the larger they are, the more light that's collected, so the fainter the objects that can be seen. And also, the larger the objective, the larger the lens, the larger the mirror, the more detail can be seen. So it's a sort of double whammy. We get more light and we get more detail. So there's always this drive towards making telescopes larger and larger. And that meant over the centuries, they've developed from objects with lenses a few centimeters in diameter to monsters with mirrors many meters in diameter. This is the 100-inch or 2.5 meter Hooker telescope. And all telescopes are referred to not by their length, but by the diameter of the main mirror, which is sitting in the bottom of the telescope down here. So that was the largest telescope in the world at the turn of the last century, operating in approximately 1918. And a few years after that, in the 1930s and 40s, the 200-inch or 5-meter telescope was built. That was the largest telescope in the world when I was born. It was the largest telescope in the world for most of my childhood. And actually, it was the largest telescope in the world for most of my adult life and was only overtaken some half a century or so later. But now we're used to the idea of not only large telescopes on Earth, but also telescopes in space, such as the now famous Hubble Space Telescope and the more recent James Webb Space Telescope launched in 2021. The Hubble is now 35 years old. Launched in 1990, it's now essentially a rather old telescope, even though it's still producing wonderful work. And the James Webb Space Telescope, launched in 2021, hopefully has got many years ahead of it. But just because we've got space telescopes doesn't mean we're not developing more telescopes on Earth. And coming along in the very near future will be this monster telescope. And I'm sure you're having difficulty getting the scale of this because you can't really tell from this. But these tiny little dots right at the bottom are people. So this telescope will have a mirror approximately 40 meters in diameter. Absolutely huge compared to any other telescope that's ever been built. More of that later. So let's think about the earliest views of the solar system from Galileo and his contemporaries. Galileo noted that our own eyes show us 4 stars which wander around Jupiter, as does the moon around the Earth. So turning his telescope on Jupiter showed him that some objects, which he assumed were probably similar to our moon around the Earth, there seemed to be moons going around Jupiter. And that was absolutely pivotal as a discovery because it shows that Earth is not the centre of the universe. Not everything orbits around the Earth. Some objects orbit around other planets. And he made observations here. The little circle is Jupiter and the little stars are the 4 moons that he saw. And night by night, he mapped out the positions of those moons relative to the disk of Jupiter. And night by night, he worked out that all of these moons go round Jupiter with different orbital periods. They're all at different distances from Jupiter. So Jupiter and its moons is like a little solar system in its own right. But the really important observation was the fact that they are not orbiting the Earth. They're orbiting something else. In a sense, Earth was relegated from the centre of the solar system and the centre of the universe to simply one of many planets. When Galileo turned the telescope on Saturn, he was somewhat confused. He wasn't too sure what he was looking at. The first sight that I had of Saturn was of 3 round stars, that in the middle considerably larger than the 2 lateral ones. Jupiter looked simply like a disk or a sphere, but what on earth is going on with Saturn? Well, that was the observation of Galileo in 1610, and that was then followed by many people for decades pointing their telescopes at Saturn, coming up with all sorts of possibilities of what it was they were looking at. Are we looking at 3 objects, a big object in the middle and a couple of spheres either side? Are we looking at a planet that's got ears? Are we looking at a planet that's got handles? There was a great deal of confusion, mainly because the telescopes were simply imperfect. It was not possible at the time to grind lenses with sufficient accuracy to give us sharp images of these distant objects. And therefore, with the aberrations that were present in the telescopes, there was a lot of distortion and hence a lot of confusion. But some decades after Galileo, Huygens postulated, well, I think all of these observations are consistent with Saturn being a spherical planet with a ring system around it. We weren't too sure at the time what the ring system was, but Huygens' hypothesis that this is what Saturn actually is, of course, has been borne out by much more recent observations where indeed we know that Saturn is essentially spherical and has a ring system. It's not a solid ring, it's a ring system made up of a huge number of tiny icy particles that are all independently orbiting the planet. There was also a great deal of confusion when people started mapping out what's going on the surface of Mars. Galileo and his contemporaries couldn't see a lot of details because the telescopes weren't that good, but Schiaparelli in the late 1800s had access to telescopes with better resolving power that could see more detail, and he mapped out features on the surface of Mars. You can see his drawings here of the whole disk on the left and some detail blown up on the right-hand page. I do like the idea that his notebook has got little bits of paper glued into it with half postage stamps. This is really frugal use of paper at the time. But the important observations of Schiaparelli was that he saw features on Mars, light areas and dark areas, contrast in other words, but he saw features which he figured were linear, these straight lines, some of them very bold, some of them doubled up, some of them rather fainter, but essentially he determined that the entire surface of Mars was covered in these straight lines, or canali as he called them, canali being the Italian for channels. So he said there are channels on Mars. But unfortunately, the word was mistranslated when it ended up in other European countries and in America. And so canali got mistranslated not as channels, but as canals. And canals has the inference that these are not natural features. If they're canals, are they irrigation systems to take water from the ice caps to the equatorial regions, perhaps? Is this indication that Mars is occupied by some intelligent creatures who are doing some irrigation? This idea was picked up by many people, including Percival Lowell, especially in the 1890s. He was absolutely convinced that these canals were artificial structures that indicated that there were Martians on Mars carrying out engineering works. And so in the early 1900s, he was popularizing this idea, such as this newspaper article in the New York Times. There can be no doubt that living beings inhabit our neighbor world. And it says in the subtitle there, Percival Lowell recognized as the greatest authority on the subject. Well, I don't know who declared that he was the greatest authority on the subject. Maybe he did. Some people believed these canals existed. Some people thought that they were illusions due to imperfect optics of the telescope. Part of the problem was that when you use a large telescope, such as this one that Lowell used, there's a picture of him in the bottom left at the eyepiece end of the telescope, a large telescope with a large lens, this one was 24 inches in diameter. When you're collecting a lot of light and it's all coming through a relatively small eyepiece at the bottom end of the telescope, if you think about what happens when you go to the optician and they shine a very bright light in your eyes to check your retina, what happens? You see the blood vessels on the back of your eye. Maybe people were getting fooled into thinking that they could see canals simply because they had concentrated a lot of light from Mars into a small disc through the eyepiece, and they were effectively illuminating what was going on the back of their retina. So some people saw these canals, but a lot of people didn't, and there was a great argument as to whether they existed or not. So the work of Schiaparelli and others indicated that there are straight lines on the surface, but other astronomers said, no, I can see the dark areas, I can see the light areas, there are definitely features there, but I don't see these straight lines that you claim to be able to see. So the original map from the late 1800s that seemed to show canals eventually was replaced with something more modern. For instance, this Hubble picture shows the best we can get from planet Earth, and that clearly shows light areas, dark areas, an ice cap there at the top, but no signs of any linear features that we can think of as canals. Some of the hysteria that existed at the end of the 1800s, of course, gave rise to H.G. Wells' War of the Worlds and the idea of being invaded by Martians. So we had the book, we had the radio broadcast, we had the films, etc. in the early part of the last century. But that has now all been put to bed. Mars appears to be a relatively dead world and is not inhabited by large tripods that are intent on invading Earth. Amateurs will always want to get the most sophisticated telescope that they can afford. And again, most amateurs try and acquire telescopes with the largest of apertures, because large aperture means collect more light, see fainter objects, and hopefully see more detail in those objects. Some telescopes, such as the ones on the left there, are called dioptric because they use lenses, but generally speaking we tend to call those refracting telescopes. And telescopes such as the one on the right use mirrors, so they're called catoptrics, but again we don't tend to use that technical term. We simply call them reflecting telescope or reflectors. But some telescopes do use a combination of glass and mirrors, effectively lenses and mirrors, and because of the two words they get concatenated together, and we call those catadioptric. A bit of a mouthful, so we tend to call those cats. So there are different types of amateur telescopes that are available, and compared to the telescopes of Galileo's day, they're not only larger aperture, they are made to much higher accuracy, much higher precision. And so when we look at Saturn, we don't see a planet with ears, we see a planet with a ring system. And this desire to go for ever larger apertures is also true for professionals. An amateur might be delighted to have a telescope like this. This is pretty much the largest telescope that an amateur can ever hope to get. And if you're having difficulty with the scale, it is absolutely enormous, and the price tag is similar. This thing weighs something like 300 kilograms. It's not really portable. Even if it's on a tripod and in principle can be moved, you really need a team of people to move it from A to B. And it's very expensive. It probably costs more than your house to buy a telescope like this. But this desire for ever larger telescopes is reflected in this particular graphic. We're looking at how the size of professional telescopes has changed in the last century or so. So this doesn't go back as far as Galileo. This is a graphic showing to scale large telescopes, but the smallest one in the top left-hand corner here, that tiny blue dot, is the largest refracting telescope with a lens about 1 meter in diameter. And you can see that when switching from glass lenses to mirrors, mirrors can be made so much larger than lenses. It's simply a technically easier thing to do. And so all of the telescopes in the last 100 years or so have been reflecting telescopes, and you can see their mirrors are enormous compared to the refracting telescopes of the previous century. If you're having difficulty with the scale, by the way, in the bottom left-hand corner, a tennis court is just peeking up there. And in the bottom right, a basketball court is showing. And for those of you who've got good eyesight, there's a human to scale. So the largest telescope in the world as it stands is Gran Telescopio Canarias. It's not circular, but we can still talk about a diameter and just imagine it as if it was circular. It's actually made of a lot of hexagonal segments, again because they're simply easier to make in lots of individual bits and then put them together than to make one large mirror. This mirror is approximately 10 meters in diameter. If we compare that with the size of telescopes that we've put into orbit, all the space telescopes are down here in the bottom left-hand corner. The bottom left in that red rectangle is the James Webb Space Telescope, a relatively large mirror, 6 meters or so, compared to the earlier space telescopes such as Gaia, Kepler and the Hubble Space Telescope, which has a relatively modest 2.5 meter, or actually 2.4 meter diameter mirror. And those aren't any larger simply because it is so difficult to put large telescopes into Earth orbit. We want to put them into space to get above the blurring effects of the Earth's atmosphere. Any telescope on the surface of the Earth will have to look through some of the Earth's atmosphere, and the Earth's atmosphere is turbulent and can blur the detail that we would like to see in these very distant objects, whether they be distant galaxies in the universe or whether they be planets in the solar system. You can see that on the right-hand side there, an absolute monster-sized mirror. Astronomers are not good at naming things, so they've called this the Extremely Large Telescope. Yeah, right. Descriptive, but not very romantic. But yes, at least it tells you it is extremely large. And you can see that from this graphic, 40 meters in diameter. It's going to dwarf even the 10-meter diameter telescopes that's currently the world's largest. It's planned for something like 2028, so it's only a few years now. It's been in construction for quite a few years. It was delayed by COVID, but hopefully it'll be operational in the next few years. As I mentioned earlier, this is the Hale telescope. It's the telescope that was the largest telescope in the world when I was born, with a 5-meter diameter mirror. This gives you a little bit of context because remember, the world's largest at the moment is twice that size. From 5 meters, you can imagine it going up to 10 meters. But the jump to 40 meters, of course, is a much bigger jump from there. We can ask, where are these big telescopes being built? Where's the best place to put an observatory to give you the clearest view of the solar system or the universe? Well, it turns out the best observatory sites in the world tend to be volcanic islands, such as, for instance, Hawaii is a very good observing site, but also the Canary Islands, another volcanic chain. La Palma and Tenerife are also host to a number of different telescopes. And the third site, which is also very good, is the very high deserts of Chile, the Atacama Desert. Being very high, you're above quite a lot of the atmosphere, and it's a very dry desert, so there's not much water vapor to absorb any of the light or scatter the light that's coming down from above. So these 3 sites tend to be where most of the really big telescopes are concentrated. And if we have a slightly closer look at Chile, you see that the marker there tells you that many of the telescopes are a little bit north of Santiago, and if we have a look at what they look like, this is a view of one observatory on a mountain top taken from another mountain top. So you can see the distant atmosphere looks a little bit hazy, a little bit cloudy, but bear in mind that's all below the telescope. The telescope's on a mountain which is above all of that haze and above a significant fraction of the atmosphere. So when it looks into the sky, when it looks up, it's only looking at through perhaps half the atmosphere that we would at lower altitudes. But still, that might not be good enough. If you wanted to reduce the amount of light absorbed or blurred by the turbulent effect of the atmosphere, you want to get even higher than a mountain top. And that is possible. Even without going into space, it's possible to get higher than a mountain top. What you need is to put your telescope in the back of a 747. And this is the Stratospheric Observatory for Infrared Astronomy. You can see from the tail splash, it's a NASA facility. They basically fly this telescope at an altitude of 10,000 meters or 12,000 meters, essentially higher than Everest, and again above most of the atmosphere. And that's particularly important if you're doing infrared astronomy rather than using visible light, because infrared light is absorbed by the atmosphere, and so you want to get as high as possible to minimize that absorption. That, by the way, has been recently decommissioned due to the James Webb Space Telescope being an infrared telescope which arguably does an even better job, and therefore SOFIA is now retired. So if you're on the lookout for a second-hand 747, watch out on eBay. It should be appearing fairly soon. But of course, if we wanted to get above the atmosphere, the best way of doing that is to put something in space. And so the iconic Hubble Space Telescope, by no means the first space telescope, but the one that is arguably the most famous, launched in 1990. It's been operating for 35 years now. Works mainly in the visible part of the spectrum. More recently, the James Webb Space Telescope launched on Christmas Day 2021. A much larger mirror, and that was rather tricky to get that to where it needs to be in space, so they built it on Earth, tested it, and then essentially folded it up, as indicated by the center panel there, folded it until it was possible to fit it on the top of a rocket and then launch it. It's not actually in orbit around the Earth. It's been parked some distance away from the Earth, about 1 million miles away from the Earth. It's parked at a particular point in space. It's called a Lagrange point number 2, and that allows it to look out into the universe, and it's some distance away from the Earth and the Moon, and it's also shielded from the Sun as well. Infrared telescopes need to operate very cold, otherwise the heat of the telescope interferes with its observations, and so it has to be kept as cold as possible, and so it's kept as far away from the Earth as is practical. So what do we see when we look out into the solar system? For instance, if we were to have a look at Jupiter, there's an image of Jupiter on the left taken with the Hubble Space Telescope, the HST, and on the right taken with the James Webb Space Telescope, the JWST. The picture on the left has this characteristic sort of reddy, browny, salmony colour, and we think that's due to particular elements and compounds that exist in the clouds of Jupiter, probably some sulfur, some phosphorus and other compounds that give it this reddish colour. We also notice that we have a lot of bands. These are produced by winds travelling in different directions, much like we have trade winds around the Earth travelling in different directions. What makes Jupiter rather different is the fact that its storm systems, such as the Great Red Spot seen here, well, these storm systems seem to last an awfully long time. The Great Red Spot has been seen for hundreds of years. We think it's persisted for about 400 years. And yet storm systems on the Earth seem to dissipate in a matter of days. So what is it that's different about Jupiter, which means storm systems can last so long? On the right-hand side, we have the James Webb image of Jupiter, a similar sort of resolution. It's a larger mirror, which in principle should show more detail, but at the longer infrared wavelengths, it turns out it's a similar level of detail as the Hubble. We can see similar systems in that we see cloud belts. It's infrared, so it's been artificially coloured to bring out different features. in the planet, but also notice this red tinge at the very top and the bottom. This is not simply an artifact. This is a genuine physical phenomena. It looks like we are seeing aurora borealis and aurora australis. We're seeing northern lights and southern lights due to interaction of particles from the sun being trapped by Jupiter's rather strong magnetic field and interacting with the cloud tops of the planet itself. So we learn different things by looking at planets in infrared and looking at them in visible light. If we look at Saturn with the Hubble Space Telescope, we get this familiar view of planet with some rather more muted bands similar to Jupiter and the wonderful ring system. But when we look in infrared, things look a little different. The planet itself looks very dark at this particular infrared wavelength, but the rings look very bright, perhaps a little surprising, until we figure out that, well, actually, at the infrared wavelength that we were using, the planet has molecules in the atmosphere that absorb that particular wavelength of infrared light, which is why the planet looks rather dull. But the rings themselves are icy particles. They are very reflective. And so any infrared being sent out from the sun is being reflected very efficiently from these ice particles in the rings, and hence the rings come out rather bright. Again, another example of how different wavelengths of light tell us different things about how the planets are put together. If we were to look at Uranus, this has been explored by spacecraft like the Voyager spacecraft. Voyager 2 went past Uranus, but bear in mind that it went past Uranus as a flyby on its way to Neptune, so it only spent a few hours flying past the planet. With telescopes on Earth, such as the JWST, we're able to look as often as we like at the planet. And in this particular case, we happen to have caught a storm system which appears to be raging, that bright spot on the left-hand side. And again, the ring system, which appear very faint in visible light, actually looks very bright in infrared light, again, because the ring system is ice particles reflecting infrared light very efficiently. And the similar story for Neptune. Here we have Neptune and a ring system. Again, some storms on Neptune by the looks of these bright spots. The rings show up rather brighter than in visible light. And in this case, it looks like a very bright star in the background. In fact, that's not a star, that's one of the moons of Neptune. It's Triton, one of its largest moons. Triton isn't that big, but it's looking really bright in this image, again for the same reason. Because it's effectively ice, it's actually solid nitrogen surface, so a nitrogen ice surface, very reflective in infrared. So even though the moon is quite small, it actually ends up reflecting as much light as the planet Neptune itself. So what's coming next? I've been describing telescopes that already exist, but there are telescopes that will be coming online fairly soon that will be game changers. One of them is this one. Almost finished construction, it's now being tested, it's now being calibrated, and it will be operational hopefully sometime next year. Originally called the Large Synoptic Survey Telescope, bit of a mouthful. It's now called the Shimonyi Telescope, and it's working in the Rubin Observatory in the Atacama Desert of Chile. It's a large survey instrument because it's going to be mapping out the sky. It's not going to be looking for particular targets. It's going to be sweeping the sky and surveying everything that's up there. It uses a huge camera. It's got an 8-meter diameter mirror and one of the world's largest cameras sitting at the front of the telescope. That gives you an idea of the camera's scale compared to a human. It's going to be carrying out a survey which they've decided to call the Legacy Survey of Space and Time. Partly so they can reuse the acronym LSST, but partly because it's a good description of the fact that they're going to be mapping out what's in space in terms of mapping out what's in the sky, and they're going to be doing it night after night after night after night and looking for things that are changing. For instance, objects moving in our solar system, asteroids and comets and other things that are moving other than the planets that we know about. It will also be looking at stars in our galaxy and other galaxies throughout the universe. It'll be looking for objects that move in our solar system, stars that might change their colour or change their brightness, and it will be looking for galaxies that change their brightness because supernovae are going off, for instance. So it'll be mapping all of these things out and then telling other telescopes which are the interesting objects to go and follow up with more detail. But this is an absolutely huge camera. If the camera in your phone has got many millions of pixels, this camera, bear in mind, has got 3 billion pixels. So in a sense, it's a 3,000 megapixel camera, and it's going to be taking images every 15 seconds, and it's going to be operating its survey for 10 years. An enormous amount of information is going to come out of this telescope, including discovery of new asteroids, and if there are more planets out there, if there is a planet beyond Pluto, this will find it. And finally, what I told you about earlier, this monster, the European extremely large telescope, perhaps you can get a better idea of scale now, should be operational in a few years. There's a couple of people in the foreground and also a couple of people standing on the platform on the right-hand side here. So remember, 40 meters across this mirror, again made of lots of individual segments. It'll be collecting so much light it will be able to see very distant objects in the universe, but if it is tasked to do so, it can also follow up any faint objects that are seen within the solar system if we think they're worth looking at in more detail, either asteroids or comets or any other planets that are out there that need more scrutiny. So if I've piqued your interest, then there are web pages that tell you all about what the Hubble has been doing for the last 35 years, how the Webb was built, how it was launched a few years ago, what its latest discoveries are, and what it will be doing in the next 5 or 10 years. And the two telescopes at the bottom are the ones I've talked about, the LSST survey telescope and the ELT, the 40-meter diameter European telescope, which will be operational soon. So those web pages there, I will send you a link to the handout so you don't need to make a note of these web addresses here and now. I'll send you a link to this handout so that you can, if you wish, follow up more about the history, what they're doing now, and what they will be doing in the near future. Thank you.